problem. All right, so miscellaneous, this topic number 1 is dealing with intensity. That sound intensity is basically power over area, that it takes a certain amount of power for energy for sound to be produced. In other words, power, again, is the amount of energy in a particular amount of time. So we can add to this power, it's basically energy per time. And so when the sound is produced, there's a certain amount of power that it takes to produce it. And assuming no energy loss in that sound wave, that's just going to basically ripple out. The area would be the area of, in essence, the sphere, the surface area of the sphere, as this, if you think about a sound wave sort of being pushed out in a sphere as it goes out. And so as it goes out, you have that certain amount of energy being spread out over a larger and larger area, and so intensity should get less the farther away you are. Which makes sense that if you connect intensity to loudness, a person is a lot louder when they're standing next to you than when they're far away, assuming they speak at the same volume. Unfortunately, people tend to get quiet when they get closer, if you're having trouble hearing, and it doesn't help. Speaking on behalf of people with hearing loss. So, now there's a threshold of intensity that the typical human can hear, and it's in units of power, which is watts per square meter. So 10 to the negative 12 watts per square meter is sort of the lower threshold there. And so let's see if things sort of match the way they're supposed to. All right, so this is a sound meter, and I can set it up anywhere along here. I've got it out to 4.5 meters. And I have a sound that's going to be generated over there. So let's put this at 250. So right now the ambient, wait for it to calm down. The ambient is somewhere in the low 40s in terms of decibels. Oh, actually, let's talk about units. Generally, when you're talking about intensity, it's always in comparison to something else. So if we take the logarithm of some intensity, say 2 over intensity 1, we're basically figuring out how much more intense this sound is over this sound. And this is just the technique that was set up, or the algorithm that was used in order to do the comparison. So if I hear, if there's a sound of 10 to the negative 5th watts per square meter, and I want to see how much more intense that is, then 10 to something to 5 times 10 to the negative 4th watts per square meter. Well, that should be 6 there for what I want to do. So how much more intense is this sound than that sound? Well, just pop into the formula there. We got the logarithm of 10 to the negative 5th over 5 times 10 to the negative 6th, which is the log of 0.5. Or logarithm of 2.
Logarithm of 2, that's 0.301, about.
301. Now, in terms of units here, this numerator had units of watts per square meter, the denominator had watts per square meter, and so mathematically the units cancel out before I take the logarithm, which it should. But we end up with a number here that actually does have units. It's similar to radians in the fact that it's a unitless unit. This is Bells.
Wait, Was this formula made by Alexander Graham Bell? I know he was that the unit's named after him, but,
Yeah, I don't know at what point this got established.
yeah, I don't know if he, I don't know if he made the formula or someone else made it, and.
I suspect that he was honored that someone else did it. Now, having something to be 0.3 bells more intense doesn't really have a lot of meaning, I think, from an everyday point of view. So this is not the most usual common unit that we work with here. Usually we don't deal in bells, we deal in decibels.
So it would be 3.01 decibels,
Yeah. So what does deci mean?
a tenth,
Nope.
10.
Deci does not mean 10. Deca means 10.
I said a tenth.
Oh,
earlier.
sorry, missed the TH at the end.
Yeah, my bad.
And so we typically deal in decibels.
Now I'm seeing how this is starting to tie in with starting to tie in a bit, because Mr. Gray went over decibels in, what was it, analog 2 or analog 1? Do you guys remember?
2.
Analog 2, he
Yeah,
talked about decibels and
Yeah, about
intensity.
Basis, the amplifier.
Alright. So, in terms of the number of decibels here, if I'm taking a tenth of this unit, I have to multiply that by 10. So basically, I'm multiplying this times 0.1 and this times 10, because I don't want to change my actual answer. And so this would be 3.01 decibels. So typically though, when you're multiplying this number by 10, the way that the formula is usually written is they just stick that out front. And so this formula right here produces bells. Or if we do 10 times the log of I2 over I1, that produces decibels, or decibels. That's about where you would put the emphasis on the syllables. Now typically if you're talking about the number of decibels, you're talking about how it's usually related to human hearing. And so when we're doing the comparison, typically we'll compare it to this threshold here. And so if I have a sound that's 10 to the negative fifth here, how many decibels is that in terms of sound hearing? Then we would do 10 times the log, and this is log base 10, of 10 to the fifth, negative fifth, over 10 to the negative 12th, which will be, I believe, 70 decibels.
So would I just do 10 log and then whatever in this calculator?
I would think so. Make sure that there's parentheses around that, because otherwise I think it'll do the log of 10 to the negative fifth and then multiply it times 10 to the negative 12th, or divide by 10 to the negative 12th.
70.
Pardon?
70.
70, okay. I forgot one thing, I will be right back, because it's one of those days. All right. So let's sort of test out sound here. Again, I have it's a sound meter. When everything was really quiet, it was sort of below 40 decibels as an ambient sound in the room, or somewhere hovering in the mid 40s, depending upon, well, sensitivity to noise. I'm gonna place something over there and about 2.5 meters away. All right, so it was about 70 decibels. I'm gonna do it again, and it is such a lovely sound. I wonder if I should just drop down the frequency, make it a little less harsh.
Really? It was, I had my headphones on.
Yeah.
I got the noises worse.
So let's try 500 hertz. Let's see what this. Yeah, it might be too small there. That's not what I wanted.
It was when we first got the thing out, it was playing different sounds.
Let's see if you can hear the version.
Is it true that,
Can't hear the highs.
this is just something I'm curious about it. Do higher frequency sounds, does the human ear, can people perceive higher frequency sounds much more easily in a loud environment over lower frequency sounds?
I think as a general rule, yes, but when you start having hearing loss, it's the higher frequency sounds that you lose first.
Oh,
So-
I gotcha.
So there's certain high frequency sounds I won't hear.
Right, I was just curious, cause I remember I would work at the food bank over at, off of, you know what food bank I'm talking about? It's,
No, but you worked at a food bank, that's good enough.
yeah, I worked with a guy, he had a pretty deep voice and, it can be kind of noisy in there with forklifts running around and stuff. So I would have trouble understanding him quite a bit of the time. So I didn't know it, that sort of led me to,
When it comes to human hearing though, it's not every frequency is heard with equal clarity, so. I mean,
that is true, I was just,
Interestingly, or noteworthy, I guess, other countries are switching the backup tones for trucks, like large machinery and stuff, to a white noise thing, because it can be played quieter and you hear where it's coming from better than a fixed tone.
Oh, huh.
they're using, white noise
Mhm.
for, interesting.
Or that you said for backing up?
Yeah, like the large machinery moving around and stuff. Because with a white noise, you know where it's coming from pretty quickly, but if it's a fixed tone, it's hard for your brain to figure out where it's coming from based on like patterns and stuff, because it's all just repeating.
Okay.
That's, that's
They
pretty
go off the
interesting.
Distant, or, yeah, I'll drop it there.
Less annoying, I think.
Was that last one 400 hertz that you were doing?
The first one was 1,000, that's 700. All right, and so also what I'm gonna do is I'm gonna hit the record button so that I don't have to, well, actually, max hold. So once I hit max hold, let's try to stay quiet. So 2.5 meters there, and hitting max hold now. 65.2. That's it, 2.5 meters away. So the distance in meters, and then, I said 62.5?
65.2.
65.2, thank you. So the question is, if I moved it to half that, to 1.25, what would you expect this to be?
You move it to where?
If I moved it to half the distance?
It's gonna be a linear, it'll be a linear increase for decibels because, it's logarithmic scale, right?
Well, let's think about the intensity here. It's power divided by area. So if the sound is being generated and it's not directional, so I think pretty much if you're 2.5 meters away, it would sound pretty much the same, I guess, other than 2.5 meters down, but the sound's being shot outwards. So imagine that for each pulse of sound, we've got this sphere with the sound on the cusp of it, at least the high pressure on the cusp of it. What does that tell you about when I am half the distance? What does that do to the area?
The error is decrease, meaning the sound intensity will increase. So the decibel is increased. The decibel will increase too.
All right, so the area will be smaller, but by how much? What is the area of a sphere? The surface area of a sphere?
Yeah.
Oh, does this have to do with the inverse square law?
So it'll be,
It has something to do with that.
Isn't it like
2 pi.
2 pi or 4 pi?
4 pi,
4 pi.
R cubed?
not for area.
For
The area of a sphere. The surface area of a sphere.
4 pi square r square.
One too many words there. Just 4 pi r squared.
Okay.
All right, so my area is 4 pi r squared. So my area, so the first one that we did there, assuming that 65.2 decibels, let's do a little plug and chug here. I know that the sound intensity compared to threshold is 10 times the log of the intensity of that last sound divided by my threshold intensity.
What is that? Beta?
The decibel will decrease.
Oh, that's the symbol that's used for the number of decibels,
Okay.
sound-wise. So divide by 10, so we have the log of I over 10 to the negative 12 is equal to 6.52. Logarithms. Now, you've had calculus before, I'm assuming you've had logarithms in some form or another.
We've seen
I think
that
that's-
be, Mr. Gray has used.
Trig.
Yeah, see,
I remember it in trig,
Okay.
yeah.
Yeah.
Alright, just a very quick and dirty logarithm. Not letting, that's sort of the 1-minute version.
It is logarithm of x equal 10 to the power of x.
Okay, so log A of, if the log base A of B is C, then A to the C equals B, basically.
Yes.
So this is a log typically is at base 10, although some math textbooks, when they use log like that, they actually mean natural log, which is at base E. But over there, if this is log base 10 of this is 6.52, so that means that I over 10 to the negative 12 is equal to 10 to the 6.52 power. So 10 raised to this is equal to that. And so I is 10 to the 6.52 times 10 to the negative 12. And what is that? I was hoping in terms of scientific notation.
Oh wait, the exponents add, right?
Yeah, but still wanted scientific notation.
3.311
Times.
times 10 to the negative 6.
The negative fifth, 6. All right. So that was the intensity of sound. What would the units be?
Watt per meter square.
Per meter squared. All right. Because those are the units of our threshold right there. All right, so we have the intensity of that last sound. That should be power divided by area. So 3.311 times 10 to the negative 6 watts per square meter should be equal to the power divided by my area, which is 4 pi times 2.5 meters squared. Close enough to 2.5 meters.
2.601.
2.601,
Yes, times 10 to the negative 4.
negative 4
Yes,
units.
watts.
All right. So that is the power that was used to generate the sound. I'm assuming that if moving this is not going to change the power, because the power is coming from here. So if I move it to 1.25 meters, we're gonna do the same thing except go in reverse, because we got the power here. So my intensity, I would expect to be 2.601 times 10 to the negative 4th watts over 4 pi times 1.25 meters squared. Yeah, I'm off there.
I'm close, 325.
325
Yes,
times 10 to the negative 5th.
yes.
And so now we can figure out the number of decibels we would expect. And so beta would be 10 times the log of 1.325 times 10 to the negative 5th watts per square meter over 10 to the negative 12th watts per square meter. What are the odds this is going to work out to what we get experimentally?
100%.
I appreciate your faith.
50%.
Look at the 80-24.
Yeah, 80.4?
80-24. No, that's not what I'm talking.
Oh, the percent chance, okay.
So, 71.222.
71.222
222.
decibels. All right, so that is our prediction, but it is physics. Who knows? It's for the excitement. All right, here we go.
This is why we rejoice.
What's that?
So this is why we rejoice.
That's absolutely.
It's exciting.
All I need is one to come out within 1% per semester per class, and I'm good.
I think you already got that one.
I know.
That one time.
So this is just gravy if this one hits. Here we go, hitting in 1 second. $72.9.
Less than 1%.
So let's find out our percent error. This is our prediction. This is our experimental. So percent error would be the difference between the two divided by the expected value. So 72.9 minus 71.2 divided by 71.2.
Is 0.024.
0.024.
Yes.
Okay, so 2.4%. I assume you did not multiply by 100.
Yeah. I do. Yeah, I know.
You did not, okay.
Yeah.
All right, so 2.4% off for physics, happiness, but not really bragging rights yet. All right, so let's do one more prediction. See, it was at 2.5. Let's shoot it out here to 4.5. Let's do our prediction. Still assuming the same amount of power over there, so the intensity of the sound that far away should be 2.601 times 10 to the negative 4th watts divided by the area of that sphere, so 4 pi times 4.5 meters squared. Around 3 times 10 to the negative 6.
Yeah, oh, well, 1.022 times 10 to the negative 6. Watt.
Oh, I realized the way I did. What were the units?
Watts per meter squared.
Doing a quick check, it is less than what we had when it was at the 2.5 meter mark, and indeed less than what we had when we were at the 1.25 meter mark. All right, so we now can predict what the decibel level is to the human ear. So 10 times the log of this number right here divided by 10 to the negative 12 watts per square meter.
I got 60.095.
60.095.
Yes, it's
I got 10.
Yes.
All right. Actually, why don't I start that first? So we're farther off here, but we're still under 10%. That's looking like, what, 6.5% or so?
6.3.
6.8?
6.3.
6.3%. So, I gotta say, not bad considering it's, physics. All right, questions about intensity? All right. The other oh, sorry, Kong?
Is the bell called an energy of sound, right?
Say it again?
Is the bell a energy of sound, right? It's called energy. The bell formula.
The
Bell formula right there.
This one,
look at this right here.
Yes.
What was your question?
It's a called energy, right?
It's related to energy of sound, but it's not, I wouldn't equate it to energy of sound, because power deals with the amount of energy per unit time of sound. And so it's related to the power and the area. There's a lot of other things built into it other than just energy.
Got it.
Yeah, okay.
Thank you.
Other questions? All right, the other miscellaneous topic, I think it's the last miscellaneous topic until I think of something else, is we talked about the Doppler effect, but that was a great opportunity to talk about the sonic boom. I don't think we did the sonic boom, did we? All right, so let's do the sonic boom. Okay, that's going. And I was originally gonna do